Dun, 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 lightning talk time.
Whoa.
Yay.
Whoa, this is so great.
There's already, the chat is flooded with puns. Let's not play it out. So everybody's ready.
I mean, I'm already ready. I'm drowning in puns, literally.
And we have to make sure that we're slightly less chaotic than yesterday somehow. And I think the best way to do that is for me to start with an hour-long talk about how I'm not Anthony Skopats.
So I think we should probably rapidly accelerate out of that and bring up our first speaker, who is Vibhu Jawa.
Who's going to talk about rapidly accelerating things?
Yeah,
Ooh.
NLP.
I get it.
So if you want to raise your hand in the chat.
Yeah, Vibhu, say hi.
Yeah, say hi so we can invite you in.
Vibhu, you're back.
Yay, can you guys hear me?
Yes.
And you're not sounding like these. Oh, I'm so happy for you. Excellent. This is so good.
Yeah. You set us up yesterday to be even more excited when we could actually hear you today. So.
Yes, look at this swarm of attention that you have right now.
So yeah, we'll let you take it away.
Awesome. Can I see my screen?
Yeah.
Hi. So I am Vibhu Jawa. I am a data scientist with Rapids. So my LinkedIn is Java Vibhu. GitHub is Vibhu Java. And this is my first time at SciPy. So really excited to be a part of this community. So let's talk about how we can use Rapids to accelerate your natural language processing workflows. So Rapids, for those who don't know, is an open source end-to-end GPU data science acceleration suite of libraries. So the vision behind this is that we want to accelerate starting from your loading phase to your model training to your model serving phase. So let's rapidly jump into the natural language processing bits of the talk. So in this talk, I am walking through a workflow where we are doing some basic pre-processing on Gutenberg dataset, and then we do some frequency analysis, and then we encode our vectors into count vectors. Then we essentially fit a KNN, and I want to show that how fast we can actually do this. So. Okay, so let's shoot. So in the whole pipeline here is just like what you're filtering pre-processing, doing a lower conversion, removing stop words, the standard pre-processing that you will expect. But on this data set, if I were to have been doing this at pandas, it would have taken me 5 minutes, 2 seconds. And I think I would have missed the talk deadline by 2 seconds. If I was doing this in DAS CPU, it would have taken me 15.25 seconds. And this is on a really meaty CPU. So it has 64 virtual cores. It's a dual 16-core CPU. And even over that, Rapids provides us a 5x speeder. Now going forward in the workflow, let's convert it into count vectors. Compare count vectors. Charles Dickens is telling stories with Once Upon a Time. Einstein is talking about space. Everything's fine in the world. Going forward, let's find who the nearest authors are. So for my modeling, what I'm using is cuML. cuML is the scikit-learn equivalent on GPUs. Again, this is a Rapids library. So as you can see, you can do almost everything end to end, and you don't end up paying the cost of transferring data from CPU to GPU to CPU again. And that's it. The workflow is complete. And we know that the nearest author on count vector space is Charles Darwin. For Charles Dickens, it's D.S. Lawrence. And that's it. So the core vision of Rapids is that we want to provide everything an end-to-end acceleration. And why do we want to do that? Is because a lot of times what as data scientists we end up doing is we kick off an ETL job, we go grab a cup of coffee, forget something, grab a cup of coffee again. So our caffeine levels really go through the roof. And the vision behind Rapids is to keep our caffeine levels at normal state so that we can enjoy a good night's sleep. That's it, guys. Have a good SciPy.
Thank you, Vibu. That was perfect. Although I mean, I like keeping my caffeine levels really high, but I appreciate how much you're thinking of our health in this time. Great talk. Thanks.
Yeah, I think I can use this for my hype performance Python.
Yeah, we'll make you extra caffeinated.
Yes, so good.
Speaking of caffeination, so Vivu, if you click on yourself and drop out, and then next up we will bring up Matthias to talk about Frappuccino.
Ooh,
Vivu was trying to bring her caffeine levels down.
Okay, I'm inviting you
in the opposite direction.
So ready. Who isn't ready for some Frappuccino?
I have 12 right next to me.
Although, I like my coffee hot, so I'm not sure I can handle some Frappuccino.
We'll find out.
Is this going to be burning my senses with some anticipation?
Yes, if you boil the Frappuccino.
Oh no!
What's the point?
Just to keep the chaos levels up. Okay.
Yes.
So can you see my screen and can you hear me?
Yes, yep. Perfectly.
Okay, perfect. Thank you. So that was a perfect transition, and I will try to keep up with the puns, which are relatively great. So hi, I'm Matthias. I'm one of the IPython and Jupyter maintainer. And so I'm going to give you a sip of one of the projects of mine that I've been brewing for the last few years, and which is called Frappuccino. If you are someone who prefers self-service, you can just see the docs here at frappuccino.readodoc.io. And if you don't like the flavor, I encourage you to come send a pull request on the GitHub repo, which is links from there. So I initially started this project after finding that it was relatively hard to find and document all API changes when making a new release of a project. And so my end goal is to have an automatic CI hook that tells you when you break API for users, so that upgrading to a new version is not too bitter for them. So I'm going to show you how I'm using that for IPython. So right now I'm on IPython master, and I want to check all the API change that have been done. So what I'm going to start doing is check out an old version of IPython. So 7.x, and now I'm going to call Frappuccino that has already been installed on my machine. It's going to grind through the IPython 7x API and put all of that into a container. So it takes a couple of seconds while it walks through all the modules, all the classes, all the objects, and so on. And so now I can come back to IPython master. So I have a developer installed, so it automatically switch which version it's going to inspect. And now I'm going to press IPython master. I'm just going to change the save to a compare flag here. And what that is going to do is compare the two APIs and give me an extract of everything that has changed, have been added, or have been removed. And so here you can see, so there are a lot of things because IPython master have changed quite a bit. You see that there are a bunch of new changes. So that are additions that you can document in the changelog or what's new. A lot of things that have been removed, disappeared, so they might have been deprecated before, and also for things that are still there, but for example, functions that have changed signature, it will tell you those functions have changed signature. And one of my goals is to develop heuristics to say, like, for example, this signature is compatible with the previous one because you're just adding a keyword argument, but this one is not because you removed argument and you replace them by an object. And so have a CI hook that automatically tell you when you do something like that. So I've been mostly working on that on my own, and you know that the best way to improve a project is to get people to use it and complain about it. So I hope you can do that and install it with pip install Frappuccino 2p2c and 1n. And with that, I will come back to the chat to let you all roast me.
Ooh, excellent. Yes, I like my roast with the most caffeine, so I'm ready for some light roast. Speaking of this, there's a new poll that some of you may see on the bottom of the screen, and very important science is happening now. So please respond. We'll do some live.
Ivanov?
Huh?
Yes, it's a poll Ivanov.
Yes, exactly. Seems like we've got lots of competition happening.
Well, thank you, Matthias. I think you've shown that research software engineers are just a machine for turning coffee into APIs. So,
ooh. Are you going to add any coffee emojis for all of your?
Yes.
Yeah, and so technically I'm a hot chocolate person, so you will have to suggest me a right emoji for that.
Yeah.
And maybe show coffee beans before and a cup after. I welcome pull requests.
Okay.
Don't press me to merge them.
Okay. Well, especially we don't want a French press. That would be dangerous.
Pardon my French.
Okay, well, thank you for the lightning talk.
And we'll let Matthias drop out, and then up next would be Matthew Petrov. If you are out there, please say hi. And then Brandon Butler would be the next person.
Okay.
So, but I feel like I should be filling out this poll as well.
Yes, I think you should.
There's no cold brew? Oh, nitro. Definitely nitro.
Yes. Okay, so let's see how the poll is doing. Some nice live commentary. It seems espresso is doing the best. I'm really upset that nobody likes complex glassware. Well, 13 people do. My chemists are very happy. Okay.
We need more organic chemists to get into the complex glassware, I think. But
ooh, yes, I think that's true. Yeah.
Hello, Matthew. Welcome. You are going to tell us about the color cycle survey update, which I'm excited to hear about as someone who has trouble differentiating colors. So great work that you've been doing so that I can actually make sense of my own plots. And we'll let you take it away.
Okay, great. I'm Matthew Petrov. I'm a grad student at Johns Hopkins, primarily studying cosmic microwave background telescope instrumentation and data analysis. However, today I'm going to be talking about my work on color cycles. A color cycle is an ordered set of colors used for categorical plotting. Essentially, it's the colors that shows up in the legend when you're making a normal line plot or scatter plot. However, many commonly used color cycles are not colorblind friendly, including some that claim to be. Here, the category 10 color cycle is shown. This is the current default in Matplotlib, as well as a number of other plotting libraries. On the left, the original unmodified color cycle is shown. In the middle, it's shown with simulated deuteranopia, which is a green deficiency. And on the right, it's shown with simulated protanopia, which is a red deficiency. These red and green deficiencies are the most common kinds of color blindness. Particular note on the right that the second and third color, the orange and the green, are difficult to differentiate, and this is one of the problems with this color cycle. So that raises the question, can we do better? Well, yes, we can. First, colors must be accessible. This can be accomplished using technical means. We can randomly generate color sets using color vision deficiency simulation to calculate and enforce a minimum perceptual distance for normal color vision, deuteranopia, protanopia, and tritanopia, where tritanopia is a blue deficiency, which is pretty rare. Essentially, this means that the colors can be told apart by the greatest number of people. So I've gone ahead and done this and generated 10,000 random 6-color sets and 10,000 random 8-color sets. A random sampling of the 6-color sets is shown here on the slide. However, we also want the colors to be aesthetically pleasing, which is obviously a matter of personal preference, which makes it much more difficult to deal with quantitative methods. So the solution I came up with for this is to do a color cycle survey. Essentially, the idea is to crowdsource aesthetic preference. This slide shows a screenshot from the survey. Essentially, the user is presented with 2 different random color sets and asked to choose their favorite color set. Once they choose their favorite color set, they're presented with 4 different possible orderings for the color set, so they can choose their preferred ordering and thus their preferred color cycle. This process repeats ad infinitum, although most users stop after around 10 responses. The survey has been available for about a year and a half now, and there have been around 17,000 responses across 1,700 user sessions. I'm currently using deep learning to analyze the survey responses using a conjoined network architecture trained in pairwise responses. Essentially, there are two identical neural networks with shared weights, and one component of the pair is given to each network. This gives you two different scores, which are then differenced and run through a nonlinear activation function, which allows the network to be trained with binary cross entropy. However, after the network is trained, you just take half the network, which outputs the score for the input. Then we use this to score the 10,000 color sets and use the scores to rank the color sets, which is a lot more efficient than trying to do some sort of pairwise ranking scheme. On the bottom of the slide shows some preliminary results. First, we start with the sets on the top. The worst sets are on the left, and the highest rated sets are on the right. And I hope you can agree that the sets on the right are more pleasing than the sets on the left. Next, we look at all possible orderings of the single highest rated set, which is what the cycle row is on the bottom. Again, the best cycles are on the right, and these best cycles based on the trained neural network start with a bluish purplish color, which makes sense given that this is similar to colors that are used at the beginning of many existing color cycles. So what are the next steps? Well, the survey is still open, so please take it. The URL is there on the slide, colorcyclesurvey.mpetrov.net. It only takes a few minutes and the results will be helpful. I'm hoping to wrap up the survey and analysis this summer. Actually, I'd originally hoped to have it done by now. I was originally planning on giving a full talk here at SciPy, but then decided it was prudent to wait to make sure I'd have the results and analysis finished in time. Once the survey is done, I'll release results, analysis notebooks, and survey data publicly. And finally, just as a general public service announcement for colorblind accessibility, please preview your plots in grayscale. If you can't read your own plot when it's in grayscale, there's a reasonable chance that colorblind individuals can't read your plot as well. Thank you.
Awesome. Thank you. That's really valuable work, and looking forward to when you have it released and look into it more.
I'm really glad we've learned, Hugh, to make some good color maps for our visualizations.
Yeah.
Yes.
I will be using those for all my categorical plots for sure.
But what is your favorite color map, David? I'm very curious.
Jet, obviously.
Oh, see, I'm a big fan of flag. I think everybody
kicked out of the conference.
Flag, even for things that are not categorical. It's really good. We now have our next speaker, I think.
Yep. Hello, everyone.
And before you start, I have created another poll for everybody to respond to. We'll leave it open for the entire talk. And again, very important science happening right now here at SciPy.
Yes, it's a very important question, I can see.
Panda in the lead already.
Wow.
Some bias. I don't know.
It's probably pandas. I mean, it's just so close.
I mean, it does, there is a good pun in there somewhere. I don't know if somebody's going to have to.
You think
I just can't bear it. I mean, the pun.
I feel like if we make puns all the time, though, it's panda ring to the audience. No, don't.
All right.
Okay.
Well,
so,
I'm going to share my screen now.
Yeah.
Yep.
All right. So today I'll be discussing recent developments in the signac framework. So a little bit about me. I'm a chemical engineering PhD candidate at the University of Michigan in Professor Sharon Glatzer's lab, and I've been a contributor to multiple open source Python packages for molecular simulations. And important for this talk, I'm a maintainer of the signac framework. So first off, why does signac exist? Well, let's imagine we have a study of binary mixtures. What does the file structure look like? So here we have one example where we have temperature varying concentration, and we store it like files like this. We have another one that has concentration first, then temperature. We have another one that's concentration and implicit temperature in some cases. And finally, we have one that has concentration, temperature, then concentration, and then concentration B, which is over specification for a binary mixture. Not only that, we actually have the wrong value here. It should be 75 to get to a 100% fraction. And we see here that when we do this manually, there are many options. There's a lot of implicit parameters that aren't stated explicitly, and it has to be user validated, or you have to come up with some fancy scheme that you then have to validate yourself. Signac is designed to automate this. From creating the data space, which you can visualize on the left, to being able to actually operate on that data space and do things like generate data, process it, and analyze. And this isn't limited to molecular simulations. The same workflow can be used for machine learning, astrology, anything that requires defining a data set or storing a data set, primarily in a file-based way, and then doing some operations upon that. This includes being able to submit to clusters. So when we go from this flow here, the workflow where we have generate, process, analyze, doing this, you could do this locally on Signac, but you also support doing this on clusters. On the code examples you see on the bottom, these are different command line operations that you can use to submit to a cluster. So if you're SSH'd into Stampede 2, for instance, and do this, this will submit your workflow on Stampede 2's nodes based on the resources you request using our framework. And so on top, you see an example workflow of modifying a given data space. So a question we could ask is, how many steps does it take to get to finalize, starting from generate? And the answer to that is it takes 5 steps, assuming that each operation counts as 1 step. So we have a branch, but they both have 2 parts to them, so it takes a total of 5. But we do know that we can get to finalize just by starting with generate. And so that's where a new feature of Signac Flow comes in, called flow groups, which take this operation graph, which we've created. As you see, it has a very graph-like structure. It is a graph, in fact. And we can take that and create arbitrary subgraphs that can then be submitted together and run together. And you can see an example in the code block on the bottom of what you would do if you created this group here that contains all the operations, called group. Before ending, we also have some up-and-coming new features and exciting new projects that are currently ongoing thanks to Google Summer of Code. We applied under NumFocus. We are a NumFocus affiliated project, so thank you. Thanks to them for that. And the 2 projects are involving 2 distinct things. One is allowing operating on arbitrary subsets of the data space rather than individual data points. So this is orthogonal to the flow group in that you can then operate on not just a single data point like temperature equals 10, pressure equals 5, but temperatures between 1 and 10 and pressures between 2 and 5. And also just improving our internal data structures that should lead to improved performance and the ability to create different backends for storage of that state point data of your data space. Here are links to our main website, our GitHub repo, and once again, we are a NumFocus affiliated project. And here is just some pictures and names of our maintainers and committers. So with that, thank you, everyone. Appreciate you guys paying attention, listening. Continue the puns.
We'll try to be punny, but there's only so much we can do.
Wait, can I respond to the talk with, this is a curse word, but DAG. That's like a directed acyclic graph.
Yeah, so Signac does allow cyclic graphs, but generally, yes, you do a directed acyclic graph.
Okay,
yes,
thank you. Thank you for making my pun almost relevant.
Wow.
I'm having trouble stopping sharing my screen here.
I will help you. There you go.
Thank you.
Yeah.
And I will.
Power, so,
I appreciate it.
Mm-hmm.
I'll let the next person go up. Thank you again.
Thanks, Brandon. Thanks for the update on Signac.
So who's next?
Who is next is Jesse. So say hi, please. He's there. He's waving.
Okay. Jesse. And as a result of our bear poll, I see that Panda got number 1, which people are very upset is not a real bear, but I would like to say that this is false. Black bear is best. And it was not an option. Sorry, everybody. Yeah, anyway.
I'm working on a library right now called, no. Jesse, you want to take it away?
Sure. I'll jump in here. Let me share my screen.
We have another poll that all you can enjoy. That's another very important question. So,
wow, people jumped right on that poll. So, weird, you didn't put Emacs, I think.
I didn't know how to exit.
All right, Jesse, we'll let you take over.
All right. So today I'm going to be talking to you about the Freshman Research Initiative, how we're charging the open source pipeline. So with that, let's start off with who am I? My name is Jesse Peisel. In previous lives, I was a quantitative geologist and a data scientist. In my current life, I'm a professor here at the Texas Institute for Discovery, Education, and Science, which is also known as TIDES, here at UT Austin. And more importantly, who do I teach? I teach pretty much all levels of undergraduates. Specifically, I kind of break them out into freshmen. My freshmen are made up of 80% computer science majors, 20% math majors. And then my sophomores, juniors, and seniors, they come from a variety of different backgrounds, art majors, engineering, nutrition, business. They're kind of a little bit more varied. So my freshmen and the rest of my undergrads, they are part of two classes that I teach here at UT. They're called the Inventors Program and the Freshman Research Initiative. Both classes have a focus on machine learning and energy. We're sponsored by ConocoPhillips, and we use the Python data science stack. Our Inventors Program has anywhere from last fall was our first time we ran it. We had 12 students. This fall, we're looking at anywhere from 35 to 40, depending on the day of the week and how many students have added or dropped the course. And then the FRI, the Freshman Research Initiative, we have anywhere from 25 to 35 freshman students. So they're literally coming straight from high school into college, and we're giving them kind of these authentic research opportunities. So the rest of my talk, I'm going to be discussing the FRI, the freshmen, as I go through this talk. So the big thing for both of these classes is that we're all open source all the time. We use the open source Python data science stack. And the big question is, how do we kind of give back? So I thought about this and thought, we've got 25 to 35 brand new college students that are excited to learn, that have all kinds of energy. So now that I'm a professor, I might as well make open source contributing part of the class. So for these students, I kind of thought of it as, how did I approach contributing when I first came to this world? It's scary. It seems really scary at first. But the big question is, how do we make it less scary? So to make it less scary, we picked just kind of a few open source projects for this spring that students could contribute to. That way students can talk to one another about what they're working on and kind of have a bigger impact as they're going through working on things. Initially, I told students they could do docstrings, functions, tests, pretty much anything that was an open issue, and let them really self-drive their projects. Once the students completed their project, which is opening or closing pretty much any issue, it was reviewed by our TAs and myself before putting in pull requests to the projects. So some of the results. So this spring in 2020, we fried some docstrings and a function. So we had 23 students that contributed to GeoStats.py, which is a Python package for geospatial interpolation. We had 2 students contribute to GeoPandas, one to Brudges, which is the bag of really useful geophysical equations and stuff. And then we had 1 student who wanted to make a PyTorch tutorial more Pythonic, and I thought that was a great option. So that's what they contributed to. And then we had a group of 4 students that contributed a 3D kriging function to GeoStats.py as well. So the last bit on results, and then I'll wrap up here. We had 27 freshmen this spring who are now open source contributors. This experience contributing early on, right as soon as they get into school, really gets them comfortable contributing. This positive that the experience that they have when they first get into this means that hopefully they'll be more likely to keep contributing as they go on through both school and into their careers. This is how we're kind of charging this contributor pipeline early on. Other bonuses that came out of this is that we have more documentation and functions for packages that we use on a day-to-day basis. For this upcoming year, I'm going to expand things a little bit more. So this fall, we'll be focusing on doc strings, examples, tutorials, kind of getting students used to contributing and how it works. And then spring 2021, going to open up a little bit more for kind of any open issues on packages. You can message me on the SciPy Slack channel, or you can message me on Twitter as well. So I'm really amped to get even more open source contributors coming in this upcoming year from these brand new freshman students.
Great. Thank you, Jesse. That's incredible. I really wish I'd had a chance to just start out doing OS contribution when I was like a freshman. So excellent. Or I mean, I guess when I was a freshman, I wish that I'd gotten fried. Let me clarify. Okay. So thank you for that. Mm-hmm. And we'll find you in Slack and on Twitter too. And then so thanks again. We'll have Wolf come up next.
Yeah, this talk rocked.
Yes, definitely.
Perfect. Thank you so much for having me. I appreciate it.
Wolf, say hi down there in the comments.
So let's check out our poll while we're waiting for Wolf. I know everybody was really into this. Wow, only 100 votes on this? Okay, well, seems like Vim is the clear winner. So
yeah.
Yeah.
The clear Vimmer.
Yeah. I like adding M's, you know? Okay, next poll, everybody, get ready. I know you're all very excited about this one.
Excellent. Hey.
Yes, excellent.
Hello.
You made it. Welcome.
Can you hear me?
Yes.
Awesome.
Okay, we'll let you take it away.
Okay, cool. So yeah, hi everyone. I wanted to talk about open software packaging for science, and it's about Mamba, Quetz, and Boa. I'm Wolf, and I work at a small company called Quantstack, and we do scientific computing in Europe. And you can find me on GitHub and Twitter, obviously. And we at Quantstack, we do a lot of work with Jupyter Lab. We have a software called Extensor, which is NumPy and C++. And then Zeus and also Mamba. And we do love Conda a lot, and we think that Conda packages are awesome. They are cross-platform, language independent, and there's a huge community around them. You can package Python, C, C++, Fortran, Rust, Go, and many other languages with Conda packages, and the Conda Forge community especially has been very successful in the past. But we did run into some troubles with the Conda solver, and sometimes it was slow and not as reliable as we wanted it to. And so what we tried to do is we created Mamba, which is a re-implementation of Conda in C++. It's basically a drop-in replacement, so all the same commands work in Mamba that work in Conda. And it's using libsolve, which is the same library that powers DNF, which is the Red Hat or Fedora package manager. You get parallel downloads and package extraction with libcurl and libarchive, and slightly better error reporting. And there's a C++ core where we implement all of this, and you can install it just if you already have Conda. You can do Conda install Mamba and then -c Conda Forge. And this is what it would look like. I'm going to skip ahead a little bit. So here I'm creating a new environment, just like with Conda, and I install a bunch of software in there. And then it parallelly downloads all of the channels and gives you a nice view of all the packages it's going to install. And then it will download all of this parallelly, and you get some progress bars and so on. Now, there's also a software that I can announce here for the first time in video. It's called MicroMamba, which is a statically linked binary. It's a very tiny version of Mamba. It's only 10 megabytes, and it can bootstrap Conda environments really quickly, and it's awesome for CI. So you just download the tarball and extract the binary, and off you go. Then one new software is Boa. And Boa is a package build tool, just like Conda build, but based on Mamba. It should be much faster, especially for large recipes with many outputs. And there's a cool color-coded console log. It's really in the pre-alpha stage. And this is what it looks like right now. So here I'm rendering a recipe for cyclic geometry. And again, it's using a Mamba solver in the backend. And you get these green and blue colors for things that have been pinned by the configuration. So here I have Python 3.6 and 3.7, and then also for run exports in blue. But this is a bit of a deep Conda stuff. And the last thing is Quetz, which is an open source package server. The anaconda.org server is not open source, but this one is. And you can host your own Conda channels, and you can have fine-grained access control, and you get OAuth integration. It's based on fast API and implemented in Python. And coming soon will be pluggable storage backend with S3, Azure, Google Cloud Storage, etc. integration, and an improved user interface. And this is what it looks like right now. So you have a small view of all of your channels, for example. And then you have a bunch of packages in each of the channel, and you can look at all the users that are registered on your system. And that's it. You can find more on github.com, the Snake Pit, which is our organization. And you can give us feedback on Gitter if you go to gitter.im/quantstack. And we've written an extensive blog post on our motivation for doing all of this here. Thanks.
All right, thank you both. And since you're at the Snake Pit, do you have a comment on our poll? What snake is most common in the Snake Pit? I'm thinking of ball python.
It all started with the Python, yeah. I'm voting for the ball python too.
As long as you're moving on Python 2.7, that's fine. Except all other Pythons. Those all look really amazing. I need to take Mamba for a test drive. So
cool. Yeah, do that.
What Mamba?
Let me know how it goes.
Do you think?
Say that again.
What Mamba do you think is the best number? I think it's Mamba number 5. I'm sorry, everybody.
I apologize again. All right. Thanks again, Wolf.
Yes, thank you, Wolf.
And Andrew is up next. A little bit of ball python in your life.
Yeah, we should redo it with Pythons. It would be so great.
Yeah, I'm going to work on that.
Okay, this Andrew. Let's see here.
He's hang.
Yes, excellent. So, there were a lot of votes for 2.7. It's only 4 votes behind ball python. So
Matt Craig says, "I'll never remember all of this." I don't know.
Thank you, Matt.
Hey, Andrew.
Hi, is everything working?
Yeah,
hear me?
We hear you. We see you.
All right, perfect. I should probably have a clock up, and I should also share.
Oh, if you don't do a clock, we'll make sure to remind you.
Yeah, I figured. Yeah, so let's see here. This should be the right tab. You should see slides. Are we seeing slides?
Yeah.
Okay, great. I guess I can start. Is everyone cool with that?
Yeah, go.
Yeah, so today I'm going to be presenting SciPy. It's a project I've been working on for a number of years, and it's a bit of a niche project, but it's been a lot of fun. So hopefully people will check it out. It's pronounced SciPy because that's just the way I have it. And there are better names that people have told me later since publishing it, but it's too late. So we're rolling with it. In my day to day, I'm in a planetary science PhD at Johns Hopkins University here in Baltimore, Maryland. So it seemed like there's other folks on the line that are in the area. So that's cool. Got my website and some links there, Twitter and GitHub, so you can check that out. So first of all, what is SPICE? Besides like just a massive Dune reference, it's a library that's produced by the Navigation and Ancillary Information Facility at the Jet Propulsion Lab at NASA out in California. And it's sort of a combination of APIs and tools to interact with planetary and spacecraft ephemeris information. What that really is the position through time of spacecraft and planets and their geometry. So it's used in like all these NASA missions to plan the trajectories of spacecraft missions, either as mission concepts or active missions, through like scientific data analysis, trying to look at spacecraft trajectories and infer spherical harmonics about the gravity of planets, and scientific visualizations. And then there's a whole slew of scientific research fields, including just like pure engineering, attitude control, prototypes to I've seen publications from the Deep Space Network from NASA and other things. So it's kind of used everywhere. It's an awesome Dune reference. And it's been in existence since like the mid 80s. So a lot of the code is written in Fortran 77 and then it's translated to C. Yeah, it's kind of an old package, but very still in use. So here's just some more examples of a graphic I stole from their website that sort of shows the sorts of things you can do, these sort of geometric event queries where I want to point my spacecraft at another thing in the sky. I know I'm going to be here at this date. Where do I need to point? How far away is it from me? Those sorts of things. So again, the purpose of this talk, SciPy, it is just a complete Pythonic interface to the SPICE toolkit. I started working on it in 2014 as sort of a correction to existential problems I had in undergraduate research, where I was working with a lot of Cassini data. And it sort of became sort of my side project until I ended my career temporarily, just took a break to do a planetary science PhD, but I was a software engineer for 2 years there. So it was sort of my side project there. In any case, there's over 600 of these functions in SPICE that needed to be wrapped. And I did it the slow and true way with C types that also allowed me to sort of fine tune the API to be a bit more Pythonic than I think you would get out of the box with something like Swig. So yeah, all the functions are unit tested. It has the CI builds and all the cool stuff. And recently it was published in the JOS Journal of Open Source Software journal. That was earlier this year in February. So yeah, and it's been used by a lot of people so far. I'm going to hide the code, although actually, I'm running up on my time. So I do have code here, but this is just an example plot I made in Folium for the Mars Curiosity rover Traverse, overlaid on a map with the high-rise 25 centimeter imagery underneath it. And those positions are extracted from the SPICE kernels, the very thing that data is written into. And SciPy is the thing that lets me get that data out and make cool visualizations like this. So thank you for listening. Here's some links. I'm also particularly interested in speeding up things on the back end. C types is great, but I would like to see some speed ups and sort of unrolling some for loops. So I'm looking into Numba and Python. So if you're an expert, reach out to me. I'd love to learn some things. So thank you.
Awesome. Thank you, Andrew.
Yes, thank you.
You've really spiced up the lightning talk. Don't laugh at that. That was great.
Well, I'm definitely not salty after that.
No.
If you want to go back through the chat later, you can see all the really bad puns.
I'm looking forward to it.
Heroic effort wrapping all that code up. So thank you.
All right, thank you. I think I just, how do I get out of this purgatory?
Click on yourself, the X.
Wow, purgatory. So I guess we're just stuck here for a while.
It's called a pungatory.
You could never escape unless you make a good pun. So we're stuck here forever.
That's my life. So Maria is up next.
We had a very contentious vote with a hot dog if a hot dog is a sandwich. It was tied between no and it's obviously a taco. So anybody wants to be the tiebreaker there, very, very good.
There's Maria.
Yep. You're on your way up, Maria.
I can't believe I missed it. There was oh, right. We're already on a different poll.
Oh, yeah. I'm just queuing up all the polls. We've got them. It's very important things happening here.
Right.
Now everybody's finding out. Maybe you all can discuss in the chat if you have a computer naming convention. So, very curious about that.
Meanwhile, we'll let Maria take over, and you're going to tell us about visualizing hidden layers in neural networks, right?
Yes, and I have a confession. I have some very bad color bars or color maps, so I apologize. They're not quite jet, but they might as well be. So I will be reaching out for some help on that once we finish up these lightning talks, and in hopes to improve my ranking or something amongst you all. I brought my dog, so I recruited my dog for some pluses.
Podcast ever. Thank you.
Yeah,
you're number one now.
Her name is Cumulus.
Oh, perfect. Yeah.
Can Cumulus be the Lightning Talk mascot? I think
so.
At least for this year.
Yeah, her head definitely doesn't look in the clouds.
She said she will do it for free. So
good.
Perfect. She wants to be an open source maintainer, apparently. All right.
Okay.
Take it away.
Awesome. All right. Well, hello, everyone. My name is Maria Molina. I'm an advanced study program postdoctoral fellow at NCAR, which is the National Center for Atmospheric Research based in Boulder, Colorado. I am a first-time SciPy attendee, so thank you for the opportunity to share some of my work with you today. And the co-authors to this work are David John Gagne and Andreas Prime, who are scientists also at NCAR. And my work focuses on, the work I'll be sharing with you is a project that I'm working on for my postdoc where I trained a deep convolutional neural network to perform an atmospheric science task. And then I ask why it's able to perform this task with skill. So the atmospheric science application in this project involves thunderstorms that occur over the United States. And thunderstorms come in many different varieties. And some of these thunderstorms have strong rotation associated with them and are isolated in space. And so because of this, these storms are more likely to be supercells, which are a type of thunderstorm that's more likely to produce hazards like tornadoes and large hail. And these hazards are a threat to human life and can cause substantial economic damage, so they are of particular interest to us. And so here we'll be focusing on classifying whether a storm within a climate data set of very high resolution is going to be a strongly rotating storm or not. And the question that we ask here is whether a deep learning model that's trained using a historical climate period can perform well when we evaluate it using thunderstorms from a future climate. And this future climate has a lot more moisture associated with it and also temperatures that are much warmer. So we're really evaluating whether extremes can be detected within a deep learning model that was trained using a current climate. And so this visualization on the left-hand side shows a current climate period. We're visualizing just a few days from the year 2011. And on the right-hand side, we can see what those days would look like in a future warmer and more moist climate. So from this high-resolution climate simulation, which is spaced at 4-kilometer grid spacing, we extract these thunderstorms. And so on the left-hand side, we see simulated radar reflectivity, where higher values can be thought of as higher precipitation rates. And we extract these storm objects throughout the entire climate simulation, as you can see in the middle plot. And I find the atmospheric variables that are associated with each of these thunderstorms that I'll be using as input to this deep learning model. And so U and V are just winds in the X and Y directions on a horizontal plane. P is pressure, T is temperature, and Q is water vapor mixing ratio. So just a measurement of moisture in the atmosphere. And I have 20 input variables because I extracted these variables across 4 different vertical heights, 1, 3, 5, and 7 kilometers above ground level. The deep learning model that I trained is shown on the top here. So it has 3 hidden layers. There's max pooling performed after each convolutional layer. And there's also batch normalization performed and spatial dropout. And this is just to help with training and to prevent overfitting. And a logistic regression is applied in the final dense layer. So the output is a value between 0 and 1. And so we're really looking at storms that are strongly rotating being a value closer to 1. On the bottom, we have 2 plots. This is just the evaluation of the deep learning model on performing this classification task. We're seeing the future climate on the left, the outlier cases within the future climate on the right. And overall, the basic way to interpret this plot is that curves that are towards the top right of that plot are performing very well at this discrimination task. CSI is critical success index, and we're just basically seeing here that this model is performing very well with outlier cases. And so now to visualize why it's performing so well, I outputted some saliency maps. And so these are visualizing the gradient of the predicted outcome from the model to some input. And so these are just examples of storms that were evaluated. On the left-hand side, I have a few just composite images of cases where the model got it right, which are true positives. We have cases where the model did not get it right, false positive. It said it was strongly rotating, but it wasn't. And there's false negative cases where it said it wasn't strongly rotating, but indeed it was. And then of course, true negatives where it just says it wasn't and it was right. And so on the right-hand side, the top row is a case that was a true positive, and saliency maps show that there's activations occurring very close to the mesocyclone of the thunderstorm, which is where that strong rotation is present. So it's really cool that this model is able to hone in on that region. And when we take a look at the bottom row, we're seeing a true negative case, and we can see that the saliency maps look very different. They're much more spread out. And I'm still trying to understand why that is. So if anyone out there is an expert on this, I would love to have a conversation about that. And here we're also visualizing certain neurons. And so some of these neurons in that final layer were activating for cases where it was saying it was strongly rotating, and other neurons were activating for other cases where it was saying that they weren't strongly rotating. So I think that there is some physical information perhaps being extracted from or being learned by this deep learning model, but still some questions as far as that. There is a poster that I have, so please feel free to check that out. And that's it.
You have perfect timing. I was going to start, making some like Jaws shark noises at you or something.
Sorry.
No, that was perfect. You ended on time. It was great. Yes. I feel like your talk had lightning within a lightning talk. So it seemed very Inception-esque.
Most lightning of all the lightning talks, definitely.
Ooh, yes, exactly. Mm-hmm. There's thunderous applause. Look at that. Yes, and also a great first-time attendee lightning talk. That was amazing.
Yeah, thrown together in like 3 hours, I think. So. Yeah,
amazing. I'm just going to let you all know, even with several days of prep, I would not be able to make something that great. So,
I spent months on my Python talk. I don't know if... Don't react to that.
Maybe we should find out. Maybe we should do a poll about Python. That could maybe be tomorrow. Let's get ready.
Save that for tomorrow. Mm-hmm. Thank you, Maria. Thomas, hey, there you are. I see you smiling.
Thomas had a smiley face. Let's see.
Up near the top.
Oh, yep, I see you. Okay. Oops.
Thomas, come back. We're going to stop talking about lightning and go back to talking about bears.
Ooh, yes. See, we've got all these polls. It's like they were constructed for this conference.
Seems like it. Who would do that?
How interesting. Yeah. And what happened with our last poll? It seems everybody's into the Monty Python. So.
Seems appropriate.
Yeah, but Monty was not a version of Python that's the best. Sorry, everybody.
Next time. Thomas, do we hear you?
Yep. Hi. Yeah.
Hey. Okay, we'll let you take it away.
All right. Hi, I'm Thomas. I'm a core dev for Scikit-learn, but I'm going to talk about Pandas' block manager today. I'm going to make this kind of interactive. So if there's any Pandas users here, could you press Y in the chat? And if you're not a Pandas user. Let's see if this works. Oh, no. Oh, that. Okay, cool. There's a delay. All right. This is going to be interesting. Cool. All right. So let's create a pandas data frame. It's a few, a million, full of ints and floats and bools and ints. The way this is stored in pandas is that they have a block manager. So there are 3 ints here and 2 floats and 1 bool. And the 3 ints are gathered together into one block, one NumPy block. And the floats are gathered together and the bools are gathered together. Now, this interface is shown with, Pandas does have an API for this, for the block manager. There's an underscore data. You can get the block manager, and if you call .blocks, you get 3 blocks in this case, 3 blocks. Now, if you look at the data frame, if you query a column and you call .values, it gets a view into the NumPy array. Now, if I add a new column to this, let's say the column int 4, what Pandas would do would add a 4th independent block representing the 4th int column. In this case, there will be 4 blocks here. Now, for fun, let's say I add a 5th column, a 5th int column. How long would this take? For those who think that it would take 1 second, press 1. For those who take 6.1 milliseconds, press 2. Oh. I timed for this. I anticipate waiting, so I don't go over 5 minutes. So people think it takes once. All right, so it's a good mixture. Nan is a great number too. I mean, so the answer is it takes milliseconds. It would be very interesting if it took 1 second. Right? And I'm adding one thing. So this takes 6.6 milliseconds, and and then there's 5 blocks. And so because I added another int column. Now, let's say I add 94 more columns. It doesn't take that much time. It takes like 560 milliseconds. There will be 100 blocks now. What happened is that I added a bunch more independent int NumPy arrays. So now the question maybe it's a trick question. If I add another int column into this data frame, how long does it take now? Press A for 1 second and B for 6.1 milliseconds. Yeah. So it's a trick question. It could be, right? Like, why would I ask this question if it wasn't a trick question? Right? So you would think, because before it took 6.1 milliseconds. Well, the answer in this case, C is not included. Yes, A. So it takes 1.3 seconds. What happens? Well, Pandas does consolidation sometimes. And in this case, it did consolidation because when I added this last column, it increases the number of blocks to above 100. So Pandas will allocate a new chunk of memory, and now there are now 3 blocks in the block manager. So it does something like this. Now, which is interesting, right? I took once. So let's for the fun of it, let's add another column. We're using lock. It takes 2 seconds. Same thing. There's now 4 blocks of memory. It used to be 3. I added a column, and now there's 4. Oh no, it's his voice. Am I above time? Oh no. Okay, so how long does this take? Oh no. Okay, it takes a second. All right. It's using ilock and I'm changing the first 10 columns, first 10 rows. And so, yeah, welcome to Block Manager magic. Yeah, there's a rewrite making it so that it doesn't do this, maybe. And yeah, thank you for listening.
Yeah, thank you.
Thank you, Thomas.
Yeah, that was excellent.
I'm glad you didn't go on any further about the internals because that would have been unbearable.
Not for 5 minutes.
Well, it seems you're everybody's favorite type of bear. So
yeah.
So thank you everybody for coming to Lightning Talks today and enjoy the drafts.
They're all great.
Yes, so good. And please sign up tomorrow. We'd love to see more of you. Again, if it's your first time, or if you are from an underrepresented group, please write that next to your name, and we'll make sure that you'll for sure get a slot.
Yeah, for sure. And there's the 2 breakout sessions that are going on right now. There's the diversity inclusion incident response, and then there's the driving hardware for instrumentation. So otherwise, we'll see everybody tomorrow for more lightning talks. So.
Yes, we'll be ready. Okay, hype. Da, 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 da.
I'm going to write 12 more polls.
Ooh, excellent. Yes, and if you have any polls you want to add, you can tell us in the Lightning Talk channel.
Yes, drop it in the Lightning Talk channel.
I'm still waiting for a cheesy talk. Nobody has done this yet, so it's,
It'd be awesome. Cheesy adventure. We need that.
We need it. I'm ready. Okay.
Okay.
Bye, everybody.
Bye.